Hello, welcome back. So, today we will have lecture 8. We will continue on gallium nitride again, and we will start from where we had left in the last lecture. If you recall, in the last lecture we introduced how the 2D electron gas is formed at the AlN-GaN interface with a basic overview of the polarization, charges and the field diagram and the energy band. We shall not discuss the transistor in detail now, because that is at a later week when we talk about gallium nitride Hemts, RF Hemts in particular in great details. So, in lecture 8 today, which is the concluding lecture on this nitride in the introductory module, we will talk about different kinds of barriers and some of the properties of the 2D electron gas in the context of polarization, and that will help us understand why and how people come up with this different kind of heterostructure designs for gallium nitride transistors. Okay, whether it is high voltage or high speed RF, people have different kind of architectures. So, we will try to just look at the properties of the 2D electron gas and see how people play with that. Okay. So, over to the whiteboard here. So, in the last lecture we talked about AlN-GaN. Now, we are in a position to actually go back and see if InGaN-GaN will give a 2D electron gas. Will it give a 2D electron gas? No, it will not give. Why? So, if you recall what I had talked in the last lecture, gallium nitride has a negative polarization charge here, the bottom you can ignore. InGaN has negative at the top, okay, spontaneous because of InGaN, and positive spontaneous at the bottom. Okay. Now, the spontaneous charge of InGaN is not very different from that of GaN. So, these quantities are not exactly going to cancel each other, but more or less close. Okay. However, if you grow a thin layer of InGaN, okay, by thin I mean, say, see, here is the context. Indium nitride has a huge 11% lattice mismatch with GaN, okay, which means you cannot grow InGaN as easily as you can grow AlGaN. InGaN will relax. Okay, and the material quality will be poor because it is also grown at a lower temperature, otherwise InGaN will decompose. So, there is a material growth restriction, and also there is a lattice mismatch restriction. So, if you suppose have indium gallium nitride of say 20% indium and 80% gallium, the lattice mismatch with gallium nitride below is so huge that this layer will relax. You do not want it to relax, it will relax. So, you want to keep it strained, only then you get the piezoelectric polarization. So, if you want to keep it strained, then this thickness, the critical thickness of this layer is very low. It at 20% InGaN it could be maybe 5 nanometer, just giving an example. It could be plus minus something, but it is very low, maybe 5 to 10 nanometer, not more. Okay. That is very thin. If you look at AlGaN, AlGaN typically say you have 20% AlGaN and 80% GaN, then you can actually grow it thicker. For instance, you can easily grow it up to say 25 to 30 nanometer, and this will not have a problem, 25 nanometer for instance, but InGaN has a problem. So, it is a 5 nanometer for instance, this is around 5 nanometer, beyond that the layer will relax, and within that it is compressively strained. But as I told you, the compressive strain of InGaN is huge. So, the compressive first point. Second point is the compressive strain is in a direction, the polarization because of compressive strain is in a direction opposite to the spontaneous polarization, which means the piezoelectric polarization will be a positive on the top and negative at the bottom, and this quantity is huge. Okay, this quantity is huge. So, if I draw the charge diagram now, okay, if I draw the charge diagram now, so this is 0, this is D, which is 5 nanometer, then you see this entire quantity on the top is positive, this entire quantity on the top is positive, and the entire quantity on the top is negative. So, here I have a huge negative charge, I will call it minus sigma p net, and the top will have a huge positive charge plus sigma p say top, and there is surface donor. So, it will make even it more, maybe, if at all there is surface donor. So, if you have a positive charge like that and a negative charge like that, forget that we do not know whether a 2D electron gas will form, we will come to that. So, what will happen is that if you have something like that, then a positive charge, unit positive charge will try to move in this direction because there is a negative charge at the bottom. So, the electric field is in this direction. If the electric field is in this direction, then electrons will try to move in this direction, which means the energy band will bend like this. Okay, right. So, the electric field is positive. So, how will the band will, I will draw it here only. So, this is 0, this is D, correct, I will use maybe black. So, the electric field will the energy band diagram will look like something like this. This is conduction band, this is valence band. Okay, because electron will roll downhill like that. That is why the field is in this direction. Okay. and InGaN this has a smaller band gap. This could be say 20% InGaN could have say maybe 2.5 electron volt or 2.8 electron volt. Okay. So, this is smaller and gallium nitride is bigger. This is gallium nitride conduction band, this is valence band, and this is 3.4 eV. So, what will happen is that at this interface, okay, you will have something like that. It will get a band diagram like that. So, there is no 2D electron gas here, no 2D electron gas. 2D, there could be a 2D hole gas, we call it 2D Hg, but 2D hole gas formation is very difficult. The crystal structure has to be very pure, and people are working on 2D hole gas for making p channel FET, in gallium nitride, but that is a different context. We are not going to talk about that because it is at a very embryonic or early stage of research, and that is not necessarily for RF right now, but you know, because whole mobility would be terrible, but 2D hole gas is notoriously difficult to form and people are trying a lot of different approach. This is certainly not the approach to grow a 2D hole gas, and you will not get a 2D hole gas because acceptor like impurities will mask that. Anyways, so you have a heterostructure something like that. Okay, so you will see that it is not giving you a 2D electron gas, and so it cannot be a transistor or a Hemt. What is Hemt? I told you Hemt stands for high electron mobility transistor because the 2D electron gas that forms here has a high electron mobility. Well, it was historically high electron because it was L-gas gas where there was no polarization, but people use modulation doping, but in gallium nitride we still call it high electron mobility transistor, although the mobility is not as high as an L-gas gas or a compound traditional compound semiconductor heterostructure. Okay. It is not as high, still we call it high electron mobility transistor. Now, okay. So, now I will only focus on those heterostructures that are more useful or more promising for an RF application. Some of them may not be commercially available, but they have been extensively researched. One such is also aluminum nitride Hemt, GaN Hemt. So, instead of L-GaN we use aluminum nitride GaN. In this case also there is a 2D electron gas that forms here, just like L-GaN-GaN. However, aluminum nitride, there are two things you need to keep in mind. Number one is that aluminum nitride polarization is much higher, okay, spontaneous as well as piezoelectric is much higher than L-GaN, okay, which means the 2D electron gas concentration, we call it 2D electron gas density, will be much higher in this case than a 2D electron gas density for L-GaN-GaN. Okay. What I mean is that if you have a traditional L-GaN-GaN Hemt, when you have a traditional L-GaN-GaN Hemt, typically the aluminum composition is between 20 to 25% and gallium composition is between 80 to 75%, and the thickness of this is also in the range of 20 to 25 nanometer, and a 2D electron gas forms here. The typical 2D electron gas density is in the range of 10 to the power 13 per centimeter square, that is the number of mobile electrons which constitute the 2D electron gas. It could be slightly lower depending on the design, it could be say 8 into 10 to the power 12 or 9 into 10 to the power 12, close to 10 to the power 13 or slightly more maybe. But with AlN GaN Hemt you get a very high density in the range of 2 to 2.5 into 10 to the power 13 per centimeter square, which is more than 2 times as an L-GaN-GaN. If your charge density is more than 2 times, then your current density also would be close to more than 2 times. So, that is a beauty, you will get much higher current. Well, the second point to keep in mind is that thickness. This AlN cannot be as thick as that of GaN because the critical thickness before it cracks, if it will relax, see AlN will relax, if AlN relaxes it is a tensile, very high tensile stress, okay, it is a very high tensile stress. So, what will happen is that it will crack, it will crack. So, you cannot grow this more than around 5 nanometer, 4 to 5 nanometer, no more, okay. So, you can get very high density of 2D electron gas, okay, but the barrier is thin. So, if you put a gate here for instance, in a transistor you need a source, you need a drain and you need a gate. The gate might leak, so that is one issue. And another issue is that we will come to that later, there is something called contact resistance, okay, we will come to that later. So, contact resistance is a problem for AlN GaN Hemt compared to L-GaN GaN Hemt. Why? Because it is a wide bandgap material, much ultra wide bandgap material. We will come to that when we talk about gallium nitride Hemt in more details. Today we are only talking about the barrier structures and the properties of the 2D electron gas. Next, this is a common structure that is also widely investigated in the RF transistor literature for gallium nitride based Hemt. And another Hemt structure is indium aluminum nitride, indium aluminum nitride barrier on top of gallium nitride substrate, for instance. Now, the beauty of indium aluminum nitride is that its polarization can be very high, spontaneous polarization can be very high, but if you put indium around 17% and aluminum around 83%, and you can calculate the polarization or the lattice mismatch at different composition of indium and aluminum. Of course, it's something, it's just plain math. People found out that if you have 70% indium and 83% aluminum, then the lattice constant A of indium aluminum nitride, lattice constant, remember, is exactly equal to the lattice constant of GaN, which means this and this are both lattice matched, both are lattice matched. Okay. If they are lattice matched, that means this layer has 0 strain for only 17% indium, 83% aluminum. There is 0 strain, which means there is 0 piezoelectric polarization, which is okay, even without 0 piezoelectric polarization. The spontaneous polarization is so high that you will get a very high 2d electron gas, and that 2d electron gas also is in the range of 2 into 10 to the power 13 per centimeter square, which is about 2 times higher than that in AlGaN-GaN. So, you will get very high charge and very high current density, okay, very high current amp per centimeter, amp per millimeter. So, indium aluminum nitride thickness also could be around 5 to 10 nanometer. You do not need much thicker. It is lattice matched, so there is no problem with growing a thick layer because there is no strain, but typically 5 to 10 nanometer is good enough, and you will get a very good sometimes 10 nanometer also, and people get a very high 2D density. This layer is heterostructure barrier is also extensively investigated for RF devices, okay, because you can have thinner barrier in both indium aluminum nitride GaN. You can have the barrier, this is the barrier, the top is called the barrier, right. So, the barrier layer is only 5 to 10 nanometer. In case of AlN GaN, we saw in the previous slide, the top barrier layer, which is this, the top barrier layer is about 5 nanometer. However, for AlGaN-GaN, the traditional AlGaN-GaN, the top barrier layer, which is this, is about 20 to 25 nanometer, and you will see that for high speed RF devices in many instances, such a thickness of 20 to 25 nanometer may not be very good. You need a very thin barrier layer. That is why indium aluminum nitride, okay, indium aluminum nitride and AlN GaN, both of these are more promising for much higher frequencies. When I say much higher frequencies, I am talking about millimeter wave. Millimeter wave typically I told you is 330 to 300 gigahertz. If you want a microwave output power, at 30 gigahertz or more, typically such AlN GaN or indium aluminum nitride GaN heterostructures are more favorable because you can have a thinner barrier. A thinner barrier is more favorable. Why? Because of reasons that we will discuss in a proper gallium nitride weak class. A thinner barrier is preferred because your channel length will be very small and you need a certain aspect ratio. These are things that we will discuss when you talk about gallium nitride Hemts in a more detail, okay. But suffices to say that AlGaN-GaN, indium aluminum nitride GaN and AlN GaN, GaN, these are 3 more popular structures that are investigated for RF microwave devices. Only AlGaN-GaN structures are available commercially either as an epitaxial wafer or as devices. AlN GaN is also now being is put out by a European company. However, AlN GaN, indium aluminum nitride GaN are for very high frequencies like millimeter wave, and they have very high strategic or military importance. So, even if people have the know how or the technology for AlN GaN or indium aluminum nitride GaN Hemt, those will most likely not be commercially available. So, for instance, in United States military radar programs, it is possible that they will have in aluminum nitride or indium aluminum nitride highly scaled W band devices. W band is 94 gigahertz for instance, which would not be available for commercial procurement, and the details also will not be available in the internet or for public. So, but it is highly speculated that AlN GaN and indium aluminum nitride GaN Hemts are most likely going to be used in such highly scaled technologies, and in such highly scaled devices, even nitrogen polar devices, about which we are not going to talk here in this course so much, Nitrogen polar devices are also very promising for reasons that we will again discuss, but in general for all typical RF frequencies S band, L band, C band, X band, etc., few gigahertz to few tens of gigahertz, typically AlN-GaN is the wafer and the material and the device of choice which is available commercially. When I say commercially available, we again have to keep in mind that there is a restriction on the import of these devices even for AlN-GaN based on the frequency and the power. So, at a certain frequency you cannot get very high power devices on the market. They are available, but they are not available to be imported by India, for instance. Okay. So, there is a military restriction on purchase of this is a very strategic technology essentially. Okay. Now, I come to the property of the 2D electron gas. Now, in all these things that is all fine, I will focus on AlN-GaN only here. Okay. I will focus on AlN-GaN. There is a 2D electron gas. This 2D electron gas is about 3 nanometer away from the interface, depends on the density, 2 to 3 nanometer, 3 to 4 nanometer, because this is your barrier, okay, this is your conduction band profile, and this is your 2D electron gas. There is a wave function, an electron has a wave function psi, remember electron has a wave function. So, the centroid of the wave function is a few nanometer. So, centroid of the wave function is a few nanometer, 2 to 3 nanometer, depends on what is the density, and typically this centroid, this delta D, the spacing between the interface, the metallurgical interface to the centroid delta D of the 2D electron gas, it varies inversely as the effective mass of electron in this gallium nitride layer. So, the effective mass of gallium nitride, the effective mass of electron in gallium nitride is around 0.2 times the free electron mass. Okay. For instance, in L-gas gas, aluminum gallium arsenide, that is a different material system we will talk about later. The effective mass is very low, it says 0.06. Because the effective mass is very low, the delta D is much larger, which means in an L-gas gas system which will look like this, the spread of the electron gas could be much larger, it could be 8 nanometer, the centroid could be 8 nanometer, just giving you a feel of that. Okay. Now, this is a wave function by the way. Okay. Now, this electron gas typically I told you is in the range of 10 to the power 13 per centimeter square. This is your 2D electron gas density. Now, this also has a mobility, electron will also have mobility, we call it mu. So, the mobility in typically we have studied in our standard semiconductor device classes that there are two factors mobility is affected by. One is impurity scattering and one is phonon scattering. Okay. So, what happens is that phonon basically is the vibration of atoms, correct. Phonon is the vibration of atoms. So, for instance, you have atoms, you can think of atoms as spring connected by spring mass, and they will vibrate, they can vibrate in this direction, they can vibrate in this direction, they can vibrate out of phase, in phase. So, there are different ways in which they can vibrate at any given temperature. The atoms in a crystal will vibrate. So, these vibrations are called phonons, and we have acoustic phonons and we have optical phonons. There are different modes in which they will vibrate and they will scatter. An electron, when it is traveling, it will be scattered by these vibrating atoms, and that scattering is called phonon scattering, that limits the electron mobility at any given temperature. With higher temperature, if you increase the temperature of the material or the surrounding whatever, your atoms will vibrate more, and so the collision or the scattering will also be more, and so your mobility will become lower as your temperature becomes higher. Now, and if you cool down the sample, if you go to lower temperature, then your vibration will reduce, and so your mobility will improve. Now, when I say these vibrating atoms are scattering the electron, it is not a physical scattering that the electron comes and hits the vibrating atom physically and scatters. That does not happen. What happens is that the vibrating atoms, which can be modeled by a spring mass system, these vibrating atoms will set up a field, okay, and we call it a perturbing field. It perturbs, the field will perturb or will disturb the electron and scatter it. So, those perturbing fields, because of the vibrating atoms, acoustic and optical phonon, they will set up different fields and they will scatter depending on several material properties. Either of them could be stronger. For instance, in gallium nitride system, optical phonon scattering becomes more prominent than acoustic phonon scattering. So, we neglect acoustic phonon scattering largely, and we can say that at room temperature optical phonon scattering is the dominant, and in also optical phonon there is a branch called the polar optical phonon, LO phonon, polar optical phonon scattering, because gallium nitride is a polar material. So, there is also something called polar optical phonon. So, polar optical phonon scattering is the most dominant scattering mechanism that will scatter the electrons of this 2D electron gas, okay, and limit the mobility. That is number 1. Number 2 is impurity. However, in gallium nitride, in this kind of a system when there is a 2D electron gas, the impurity scattering actually is very negligible, because typically you have a bulk semiconductor which is n-type doped. The electrons coexist with the impurities, and so they get scattered a lot. Here we have not added any dopant. Did we add any dopant? No, we did not add any n-type dopant, we did not add any p-type dopant. So, this is a dopant free material. If there is no dopant, how will they scatter? Correct? This electron gas that is there is no dopant anywhere near it, we have not added the dopant. However, in the gallium nitride crystal, when you grow the material, does not matter how sophisticated your tool is, how ultra high vacuum you are using, there will always be some background. There will always be some background impurities. These background impurities make the gallium nitride mildly n-type doped. Okay? These background impurities make the material mildly n-type doped, mildly, very mildly, say 10 to the power 16 per centimeter cube could be your background impurity. So, the background impurity has background ions, you are not intentionally adding them, they are unintentional. We call them UID, unintentionally doped, you cannot avoid that. So, these background impurities could be, for instance, say carbon, could be oxygen, could be even silicon if you are growing on silicon, for instance. So, these background impurities are very lower in quantity, and that is depends on the growth technique also and the growth approach, what kind of growth optimizations you have done, because if you have not perfected the material growth properly, you can have very large number of impurities which will be very bad for your device. But in general, in a well calibrated system with a lot of experience, people develop this crystal growth techniques where they manage this background impurity, and you can get to very low background impurity concentration in the material, but still there is some background. So, those background will try to scatter the 2D electron gas, except that they do not scatter as much, because number 1, those background concentrations are low, correct. So, the scattering will also be low, and secondly, when you have a 2D electron gas, you have something called screening. 2D electron gas density is very large, it is not metallic, but it is approaching that, it is very large density 10 to the power 13. So, when you have a very large density of 2D sheet of electron, they can screen the electric field like a metal, and because they can screen the electric field, the scattering because of impurities can be reduced. Okay. So, that is why the impurity scattering mechanism is not so critical for this heterostructure, it is only the phonon scattering that limits the mobility. Okay. So, if people can do theoretically, they can calculate exactly this polar LO phonon scattering, okay, what is the theoretical limit to which this polar phonon scattering will affect the mobility of the 2D electron gas formed at an AlN-GaN interface, and people found out this is in the range of 22 to 2300 centimeter square per volt second. This is the at room temperature at 300 Kelvin. At 300 Kelvin, the maximum mobility theoretically you can get is 22 to 2300 centimeter square per volt second, which is the polar optical phonon scattering, and you cannot beat that at room temperature because the atoms will vibrate so much at the room temperature. However, when people are starting to grow very good crystal of AlN-GaN, they are not getting this mobility, they were getting lower, maybe say 1600 or something like that. Okay. Then they realized that there is a third scattering mechanism. Second is impurity, which did not play a role, first is phonon, which is the most important. The third scattering is called alloy scattering, and this is a very unique scattering mechanism. What happens is that because you have an AlN-GaN Hemt, the way it is drawn is something like that, right, and you have the electron gas in here, The electron the electron wave function can also penetrate to some extent in the AlGaN. This is your AlGaN. The electron wave function, a part of the electron wave function also exists inside AlGaN, okay, because it tunnels, although it is a barrier, but it can tunnel. Now this fraction of the electron that is inside the AlGaN, it suffers alloy scattering. What it means is that alloy is an ternary compound, aluminum gallium nitride. There will be alloy fluctuations, okay. What it means is that there is aluminum and there is gallium, there are two different species of group 3 atoms that will occupy these group 3 sites. There can be a non-uniform arrangement, it is a fluctuation of the alloys that can happen at the atomic scale, because of which there is a potential. An atomic fluctuation of alloy sets up a potential, because it is not a binary alloy, it is a random alloy, it is a random alloy. Because of this random alloy, you have a potential that is set up that will also scatter electrons, okay, that will also scatter electrons, and this results in an alloy scattering, and that is the reason why people were not able to get up to this high mobility. So how do you solve it? The way you solve it gives you two benefits. One is that it increases your charge density of the 2d electron gas, and secondly it removes alloy scattering and helps improve the mobility. So what you do is that you have this AlGaN, you have this GaN, in between you have a thin layer of AlN, a thin layer of AlN which could be 1 to 2 nanometer, not more, a thin layer of AlN. So how will the band diagram look like? The band diagram will look like something like that. If this is a Fermi level, okay, maybe I will draw in the next slide, okay. So suppose this is your Fermi level, right, this is your AlGaN. The AlGaN now band will bend in the opposite direction because there is AlN. AlN has a very large band gap. This is your AlN band gap. This is GaN. This is AlN. AlN has a very large band gap, 6.1 electron volt, and this is AlGaN. The AlGaN band is bending opposite because there is an AlN which has very large negative polarization, okay, and a very large positive polarization here. So this delta EC, this is delta EC for AlN and GaN, it is very huge, and because it is huge, the electron gas here cannot penetrate here, cannot penetrate, cannot tunnel. Why? Because if you remember a quantum well, if this is deep, the electrons cannot tunnel. Only if it is shallow, electrons can tunnel. So by having AlN, you are creating a very deep potential, so electrons cannot tunnel because it is a very deep potential. Electrons will have very low probability of tunneling. Secondly, this AlN is a binary, it is not a ternary, it is a binary alloy, so it has no alloy scattering. Even if electron tunnels a little bit, which is very unlikely, it will see a binary alloy which is does not have any random alloy fluctuation. You have separated the random alloy, from the 2d electron gas here. So number 1, tunneling reduces, almost becomes 0, correct, and number 2, it is a binary alloy, so there is no alloy scattering even if it tunnels. It helps people report to up to 2200 centimeter square per volt second very easily, okay. People get routinely more than 2000 in commercial sample, okay, and because there is AlN, the polarization is very high, although it is not 5 nanometer. If you had 5 nanometer, you would have gotten 2 into 10 to the power 13, but that is not the point here. You will still get like 1.2 or 1.3 into 10 to the power 13 per centimeter square. So that is a very good charge density, that is a very good mobility, okay. It is all at room temperature, by the way, okay. And so this 2dG density has something called a sheet resistance. Sheet resistance should be as low as possible. Sheet resistance basically has the unit of ohm per square. Why square? Because if I look from the top, and this is a wafer for instance, if I have a metal pad like that, if I have another metal pad like that, imagine that they are isolated, okay, this is a metal pad, this is a metal pad. If this is your W and this spacing between them is L, Okay. This spacing between them is L. Then essentially how many W's can you fit in here, that is your W by L. Okay. How many, or you can add sorry, L by W. L by W tells you how many W's can you fit. So, what I mean is that if this is suppose 20 micron and this is could be say 10 micron, this is 20 micron, and the spacing between two metal pad is suppose 100 micron, L is 100 micron. So, 100 by 20 is 5. So, there are 5 squares inside this active area. This is important for 2D transport actually, because current will flow laterally, or okay, the unit of current is amp per millimeter or milliamp per millimeter. So, talking about 5 squares here. So, what happens is that if the sheet resistance is suppose some value say 300 ohm per square, that is the unit you will tell, the total resistance between these two pads, okay, maybe I can erase it here and then show it again. The total resistance drop that is happening here, the total resistance is the sheet resistance multiplied by the number of squares. So, 300 ohm per square into number of square, here it is 5 because there is 100 and this is 25. So, this is 1500 ohm absolute units. Okay. So, this region has a total resistance of 1500 ohm. Square does not have dimension, but it is a unit nevertheless. Okay. So, RSH into L by W tells you the total resistance. Alright. So, the sheet resistance is a very important quantity, and this is given by 1 by charge of electron times the mobility times the 2D electron gas density. So, if you have a higher mobility and a higher 2D electron gas density, the sheet resistance becomes lower. It is desirable to have low sheet resistance because it helps reduce parasitic components. It also helps reduce the unnecessary parasitic resistance drops called the excess resistance, and it helps improve the overall on resistance of the device. Okay. And you want it to be as low as possible, which is why you want a high mobility and high 2D density. Alright. So, the take home exercise today would be that if you have a 10 to the power 13 per centimeter square of electron, the charge of electron you know, and you have a mobility of 2000, how much is the sheet resistance coming out to be? You can calculate, and you will find out from this expression that the sheet resistance comes out to be around 310 or something ohm per square. So, that is a good one. Commercially you can buy AlN-GaN Hemt whose sheet resistance is 300 or less than 300, 290 ohm per square. Commercially you can buy, these are well qualified, verified, calibrated. Academically people have researched and gone even below 200, there are techniques 150 ohm per square using AlN GaN. Okay. People have gone even less than 100 by using multi-channel 2DEG, but we will not talk about that here. So, it is possible, okay, and this 300 is a good number. You should not be much higher than 300 ohm per square if you are talking about an RF device. When you make an RF transistor based on AlN GaN, you should try to see that the material you are using or the Hemt you are using should not have a sheet resistance much more than 300. It should be 300, maybe 310, lower than 300 preferably. That should give you a good RF device, provided many other conditions are met. But this is the on resist the sheet resistance part of the AlN GaN Hemt. Okay. And because it is a quantum well, the 2D electron gas, concentration does not depend on temperature, If you heat the sample, mobility will decrease. If you cool the sample, mobility will improve, but the 2D electron gas concentration say 10 to the power 13 will not change if you heat the sample or if you cool the sample. It will not freeze out, because the conduction band, if you recall, the conduction band here you can see this is your Fermi level, the conduction band goes below the Fermi level, so this is degenerate, this is a degenerate electron gas, this will not freeze. At very low temperature, at cryogenic temperature like 4 Kelvin, millikelvin, your AlN GaN Hemt will have very high charge density and very high mobility. So, your current density will be much better at lower temperature than at room temperature. Okay, that is a very good beauty. So, you can use gallium nitride devices for cryogenic application, whether it is RF or power switching. Okay, that is a very interesting point. You should know that 2D density does not change with temperature. Okay. So, I think with that we have covered enough of AlN GaN Hemt basic structures, and we will conclude lecture 8 here. So, we have given a very simple and a quick overview of different kind of heterostructures in this lecture: AlN GaN, indium aluminum nitride GaN, AlN GaN. There is a critical thickness of course, and there is a composition, and the scattering mechanisms and what is a typical 2D electron gas density, what is a typical electron mobility in these heterostructures. We are just getting started, and there is a lot more things that will come in this kind of heterostructures in a separate week, but this is the basic concept of a 2D electron gas, which will stay similar when you talk about L-gas also. But in L-gas heterostructure we do not have modulation, we do not have polarization, so we have to use modulation doping, that is a different concept. But in lecture 8 we have concluded the first hand and the quick overview of III-nitride alloys and polarization and Hemt. Okay. In lecture 9 and 10 of this week, which is going to be the last lectures of this week too, we will study about Schottky multipliers and varactors. So until then, goodbye and have a nice time. Okay. Thank you.